In one, two, three. Yes. All right. Thank you everyone for joining this section. My name is Levinus. I am with the Information Security and Communication Department here in NTNU. And I'm working with Steven. I'm a PhD candidate working with Steven Wurtzen. And I will be presenting my ongoing research activities. And the whole idea is to motivate you so that when you think about, so that to motivate you to, when you start thinking about your master's thesis, then maybe some of the ideas that we presented in this short presentation would help you. Maybe some of the topics you could investigate during your thesis. That is the whole idea. So, outline of this presentation. First, I would give a general overview, introduction to motivate the problem, then define what exactly is software-defined networking and why is it important. Then we'll look at the application of software-defined networking in industrial control networks and some of the results that we've been able to obtain so far in the course of our work. And I'll proceed to conclude this presentation. All right. Something interesting happened during this COVID-19 period. Those periods where everyone was on lockdown. You remember that, right? I guess all of us experienced that. We were on lockdown and everybody was at home. And one thing happened. Due to the fact that everybody was at home, most people spent their time watching movies online. And that cost something. It skyrocketed the number of people using the internet. Because nobody imagined when designing the internet, there will be a time a pandemic will force all of us to stay back and watch movies. Nobody anticipated that. But the COVID-19 made that happen. And we obtained some interesting results this period. Now look at this definition, what this news article said. It said that AT&T is one of the biggest providers around the world, also is located in the US. Now, they were able to dynamically scale their infrastructure in such a way that they were able to accommodate the increase in internet traffic. This is something that is practically impossible if you're using the current network infrastructure. It is only the software-defined networking that would allow you to do that. That is amazing. That is amazing results. That's why you can see they said that you don't design a network for a pandemic. But it turns out that building your network on software and open hardware specification can help you make it ready for just about anything. This is the CEO of NTNT making this comment. And you might be wondering, and some of us over there in Trondheim and those watching even at home might be wondering, what exactly is SDN? Now, SDN is a networking architecture where we abstract or where we remove the control from the data plane such that the data networking devices become just forwarding devices. The instructions being forwarded to them from the control layer. In the current networking architecture, what we have is that the control and everything is built on the networking hardware. Everything is on the networking hardware. And SDN takes this approach. What it does, it opens it up. this way. Can you see this now? This is what we have in SDN. SDN opens up, initially we have the networking devices embedded, the control and the forwarding function is embedded in the networking devices. That's the router. You know the routers, right? The routers have the function, the control function and the forwarding instructions are embedded in the router. So what we do in SDN is to remove those functions, the control function, from the router so that they are just forwarding devices. And all the instructions on them will be forwarded to them from the controller. This is an important innovation that has not happened in a very long while. Because in the computing world, we've already achieved similar results. In the computing world, we have the operating system. You remember the operating system, right? And you install the operating system on the hardware in a way that the hardware is abstracted from the operating system. So you don't need to know what is happening in the hardware. What you just need to do is to design applications that you can just install on the operating system, and whatever happens underneath is no longer your business. So it introduces innovation. People are able to write programs using normal Java and other applications, and they run it on an operating system, and the operating system does the remaining work. The same thing we're trying to do here in networking. We want to introduce programmability such that I just write programs or write instructions for the network on the application layer. And I don't longer care what happens underneath the forwarding. So when I write that program using the network operating system, right, it helps me do the other remaining function because the control has abstracted what is happening within this place. Do you get the idea now? So if you look at this, exactly we have this finally, which is the SDN architecture. We have the application layer, the control layer, and infrastructure layer. In the application layer, you can now write programs that the control layer would help you implement and forward them to the infrastructure layer. So now we open it up. Ability to program dynamic configurations. You can integrate it with network function virtualization and the dynamic scaling of the infrastructure, which was achieved by AT&T during this coronavirus, was because of this. Do you get it now? So now the question is, can we replicate this for industrial control networks? Is it possible? That's the next thing we're asking. Because now, following the deployment of SDN by Google, Facebook, across their databases, there has been interest to exploit this to also do the same for industrial control networks. But the difference between these two networks is that in the normal network that we have in Google, Facebook, and the normal ones we're using, these are best effort delivery, right? But in industrial control networks, we have an issue. The correctness of the application or the correctness of any function applied there is time-bound. So you need to meet some guarantees. There is quality of service requirements that needs to be met. So if you're deploying any infrastructure for industrial control networks, it should also take into account that these guarantees are very important and they need to be met. So this is the constraint that we have to work with. This is the constraint we need to consider, we need to think about before we implement SDN for industrial control networks. Even though it could be very interesting to see how that is going to work, we also need to know that industrial control networks are critical systems, such that if there is any failure on those systems, it could even endanger the life of humans operating those systems. So, in order to do the evaluation, you need to think about a much more easier way that would not endanger, because you don't want to run it in the actual when it is still operating. You need to evaluate it outside. Ensure that it's okay before you start implementing. So before we talk about the ways to evaluate the applicability of SDN for industrial control networks, let's look. This is a typical picture of a proposed architecture for SDN applied to a smart grid. Here you can see the SCADA system. Here you can see the controller. Here you can see the application. So this is just a typical illustration, a typical model of how you can deploy SDN for a smart grid. Now we'll go back to our previous question that we were asking. How can we guarantee that these performance requirements will be met? There are several ways of doing that. First, it is either you build the actual system and take measurements. This is it's not cost effective, because if you're building the whole system, you know how much it's going to cost you to build the system. What if after building the system and you don't get the result you expect? You've lost, you will have to start counting your losses, right? Then another way is to run simulation. That is, imitate the actual system and evaluate it to see if it is going to meet those performance requirements. Then a third way is to do analytical modeling, where you use mathematical tools to reason about or to evaluate the performance of these systems. So, analytical modeling allows you to evaluate wider configurations, right? I'm not saying this because my research area actually falls within this, but it is very true. You can explore you can evaluate the performance of several systems using analytical methods. Then in my own research, what I do is to use keying theoretical frameworks and process algebraic methods to investigate this problem. So this is what I do. And I would proceed now to look at some of the results I have obtained so far in the course of my research. So because of time, just about 3 of them will be presented here. So first, like every other research, the first thing you do is to evaluate what others have done. Now, in this paper, what we did was to review the use of queuing networks in evaluating software-defined networks. Now, from our review, we discovered that several people have, done performance analysis of SDN using queuing networks, but none of them have considered in a situation where adversarial actions might occur. And what we did was to propose a much more precise way of characterizing the arrival processes and the service distribution for a situation where adversarial actions could occur. And we proposed like 2 different methods that can be used to study this behavior. So this work was presented at a conference in the US in Hawaii, right? And this was done with my supervisor and myself. Then in the next one, in this paper, what we did was to take one of this model. Remember, in the previous paper, 2 models were proposed. Models that could be used to evaluate how adversarial actions could occur. So what we do was to use one of these proposed models and to study attacks, to study adversarial flow in software-defined industrial control networks. Now, this work provides insight for benchmarking and would also facilitate the identification of factors that could cause a network to breach the quality of service requirement. A very important result that we obtain here is that an attacker with some knowledge of the network, with some knowledge, can cause the system to breach its quality of service requirement by increasing the arrival rate. By increasing the arrival rate of the adversarial flow in such a way that it is a bit higher. And he can also continue to do that until it causes the network to breach the quality of service requirement. So this is the result that we obtained here. And this work was also presented this year at a conference in France. Then, another interesting paper too that we presented this year was adversarial model for attacks against IEC 61850 real-time communication protocol. IAC, in this case, what we are looking at is the application level, just the application level. Because the area of application that is much more for interest for us is the power grid. So there is a protocol called IEC 61850 that it's used for power automation. So in this case, what we did was we observed that the conventional adversarial models, they are not sufficient to model the attacks that could be targeted at this protocol due to its unique nature. So we proposed using PyCalculus ways these attacks could be reasoned. Where an attacker can be able to, attack this particular system because it has some unique properties that is not captured by the conventional adversarial models. So in this case, we also went ahead to show the utility of our model using a replay attack that could cause a denial of service attack. So this is the general results. Just an overview of the results we've obtained so far in my work. And just to conclude, to allow you time to ask some questions. Now, research and applicability of SDN for industrial control network is just still ongoing. It's still because we are not still sure if the success that was achieved in the data center and in other areas could also be replicated for industrial control networks. So, and if you watch very well, you will see that some of this industrial control networks is part of a broader area called cyber-physical systems. Cyber-physical systems are actually systems that integrate both the computational power, communication to control physical devices, right? And you can find it almost in most places, especially in the power sector, in the telecommunication sector too. You also find them in the medical sector, right? IoTs and all that. They are all grouped in cyber-physical systems. Now, my work also extends to those areas. And currently, I am also investigating how to use the expressive power of PyCalculus to reason about attacks against cyber-physical systems. So this is what I am doing in my research work, and hope I have been able to motivate you to, when thinking about your by next year, I guess, you'll be thinking about your thesis. You remember, and you could chat me up or talk to me if you want help and want to also investigate cases or anything related to SDN, or you want to use some mathematical models to reason about the performance of physical systems. So if there are questions, you're welcome to ask me. Thank you.
Actually, these students are in their first semester.
Okay.
They might be looking for the PhD thesis in their fourth semester, that means in the next year.
Yeah, yeah.
And I think they might be interested to know if you will be there at that time and what are the likely topics.
Yeah, I think I will still be here by next year.